So welcome again to the Green Bank Community Zoom. It's great to have so many folks joining in on this. So I'm Karen O'Neill. I'm the director, if you don't know me, and I'm going to start off first with just a brief overview of the observatory and where we're at with Green Bank, and then I'll turn it over to Jay Lockman after that, who'll talk a little bit about the upcoming proposal deadline. And then we have a great treat here. We've got Brian Svoboda talking to us a little bit about some of the science he's been doing with GBT. So let me just start off with just a quick overview of what's going on under the pandemic and with COVID with the observatory. West Virginia, like many parts of the United States, is now experiencing a rapid increase in the COVID-19. And this is being measured in terms of just the percentage of cases that are positive. So how many tests you have and how many of those are positive. So we're on a fairly large upswing at the moment, as you can see in the chart on this plot. The result is the restrictions for the state are starting to pick up again, with masks being required indoors and a lot of restrictions for gatherings, no gatherings above about 25 people. And within the county itself, we've also had a lot of new cases. That's the bad news. The good news is many of these restrictions have already been in place all along within the observatory, and so we feel quite confident with the safety of our staff here on site. So we moved over to what we call a return to full operations status on June the 6th. And the result of that is that we have all of our telescopes fully operating, all operations in place, receiver changes are occurring, operations are occurring, and all of our instrument development programs are also fully underway. So everything is moving forward, which is fantastic. But work is a little bit slower than it used to be, but we'll appreciate that slowness because it means that staff are working safely. So things take a little bit longer. Everything's just a little bit more time to make things happen. But the great news is that all of our staff have been working carefully to make sure things are happening and all of the telescope operations are moving forward. Having said that, though, of course, all of our visitor programs are still canceled. Some of our summer educational activities have been moved to remote, such as the Pulsar Search Collaboratory training in the summer and a few things like that. But unfortunately, a lot of our educational activities have been canceled, and certainly the Science Center, our tour center, is still closed, and all of our visitor tours are still on hold until we can find a good, safe way, not only for our staff, but for all of the visitors to come on site. The good news is, though, our summer students, the REU students, the PING students, and our summer interns have been able to work remotely with a little bit of creativity on the part of our computing division and others. And we're able to give them a lot of their summer experience, even if it's not the full summer experience on site. And with that, I just want to mention a couple of upcoming events at the observatory. So the first one is the workshop 44, a proposed instrument for the GBT. The workshop is in the end of September. The abstract deadline has passed, but of course registration for the meeting has not passed, and I encourage everybody to come and register online for this and learn more about the science or contribute some of the science that could be done with the Argus 144 instrument. Additionally, the observer training workshop that was scheduled for the fall has of course been moved to a remote training workshop. The registration for that is now fully open. And again, anybody who wants to refresh our course on using the GBT or would like to learn how to use the GBT for their observations is strongly encouraged to register for this event. Again, both events will be held virtually using Zoom online, and we're confident, though, with now many months of experience in organizing these, that this will go very well. And that's really the news that I wanted to put out there, and just let you know that all of our fantastic scientific staff are still working. They're just working remotely in this. And with that, I will say if there are any questions, feel free to put them in the chat window. And if not, I will hand this off to Jay Lockman to talk a little bit about our proposals and what's going on with our proposal call. So off to you, Jay. I believe Jay is getting things up, but Jay is still muted, so I'll do a little song and dance routine while we wait for Jay here. Or Jay could do a song and dance and mime of his slides as he pulls them up, which hopefully will happen soon. Again, I'll say, as Jay is trying to get things up and running, that for both of our Observers Workshop and the Argus 144, if you didn't catch the specific registration website, just go to our main web page and you'll be able to find those. And now I believe we have Jay.
Yes. Can I share screen, Marty?
You should be able to just do it, Jay. Should be all
Okay,
set up.
good. We'll see what's happening here. Okay, are you seeing the Green Bank Observatory call for proposals?
Yes, indeed. You're
Yes.
up and your screen is shared, Jay. You're
Yep.
good.
Great. Well, Tony Minter is unable to discuss this today, so I've taken his place. The call for proposals for the 2021A semester has gone out, and I'm showing you here how it looks if you follow the link on our website. If you go to our main website, you can get to the link by going to the upper left. It's one of the headlines up there, or just follow through on the science section down to proposals. And there are a few things new about this. First of all, the deadline will be on August 3rd at 5 p.m. Eastern Time. We will not be accepting large proposals at this call for proposals. From now on, large proposals will only be accepted at the February call. And this is to even out the playing field for those who are applying for this time. So a couple of new things are joint observations with SOFIA. We've got an understanding now with the SOFIA Observatory that they can award some fraction of the GBO Open Skies observing time for projects whose primary instrument is SOFIA, but can benefit by having some relatively small amounts of GBT time. So proposals in this category would be submitted only to SOFIA, and their TAC, if they approve them, will communicate to us, and the time, barring technical problems, will be given. At the same time, applying to the GBT for telescope time that can benefit from a regular small amount of time on SOFIA can apply just to the GBT with this note, and time will be given on SOFIA. There are some restrictions, so just go and take a look at the joint observations page for more information on this. But just to remind you, we already have joint observations through Hubble. Here's the list: XMM Newton, Chandra, Hubble, Swift, and Fermi. And so in all these cases, you apply the primary instrument, and then the time on the secondary instrument comes with it without the needing to apply. I must say there are some restrictions, and in particular, if you have projects that require coordination, observing at very specific times, or coordination with other instruments, then you may have to get those through both TACs. And that's all I had, and I'd be happy to take questions or comments if there are any.
So yeah, there's a question from Patrick Taylor, said planning to submit a white paper to Planetary Science Decadal Survey today, advocating for planetary radar for single disc radio telescopes. Would like to include a sentence on NSF's current funding profile for GBO. Patrick, that's something that I can respond to. I'll send you an email after the meeting today. There was also a question from Jose. He said last meeting it was scheduled a talk on pulsars, but it was not discussed. Will this be scheduled for next time?
We're trying to go to a new format for these, where we'll keep the news about the GBO fairly short at the beginning, and then have a 15-minute science talk. And I might also say that next time we should be in a webinar format rather than a regular Zoom format. And this will allow registration up to the last minute, including while the session is underway. So that should make these sessions less clunky. And 2 weeks from now, on our next session, there will, I think, on Shapiro delay observations of pulsars with the GBT. So that pulsar talk will take place 2 weeks from today. Anything else, Marty? You good?
Just one last question from Richard. Is GBO still on contract with the breakthrough list? And the answer to that is yes.
Yeah, so these shared proposals, by the way, with the other instruments only refer to the amount of open skies time that's available. Okay, I'm going to stop sharing and turn it over to Brian, our speaker for today. I might as well. Let me introduce you, Brian, for a second. Brian Svoboda is a Jansky Fellow who is in residence in Charlottesville. And he's talking today about, what, pardon?
Socorro, but actually technically I'm in residence in Puyallup, Washington at the moment.
Oh, I'm sorry.
because of COVID.
Right.
Although it's okay.
Okay, I'll let you take it over.
Oh, sure. Sure thing. Here, let's see. Okay. Hopefully my screen has been shared. I will assume that it has.
Yes, we can see it.
Okay, well, it's absolutely amazing that these things work on Linux. It's like a miracle every day. Well, great. Thank you everyone for joining us for this webinar today. I'm really looking forward to being able to discuss some of the research that I've been working on, as well as some really cool and exciting things I think we'll have to look forward to in the near future with the GBT and other next generation facilities. And I've titled my talk Towards a Multiscale View of the Dense Gas in Our Galaxy, the Milky Way. And shown in this cover slide here is just absolutely gorgeous data from the Green Bank Ammonia Survey, so this is the molecule ammonia, with, I believe, some optical data, or maybe near UV, of Orion, the Great Orion Nebula in the background, along with the very famous Orion A molecular cloud integral-shaped filament in the background. And this is the kind of object that I'll be discussing today, these molecular clouds of dense cold gas that go on to form stars. Let me just, how do I change? Okay, and what I mean by multiscale in this case is that we have the tools from radio interferometers and radio single dish telescopes to observe star formation at a variety of both the small scales relevant to individual protostars. Here I've also shown this fantastic data taken by Alvaro Hacar towards also Orion. This is closer, you can see the trapezium in the upper left corner here. It's on its side, so if it's on the page. But this is of the molecule N2H+, just showing the exquisite filamentary structure that you can observe with the fidelity of ALMA in these streamers and subfilament type small filaments that are characteristic of the type of gas that we're observing. But the opposite side of the multiscale is also something that has been really powerfully enabled by ALMA, is observing at the large scales that on the opposite side of sort of the 0.1 parsec and smaller individual protostars and the gas around them, we also have the extragalactic scales. So this is a image that I've taken from a white paper by Eric Rosolowski 2019, but it is FANG's data, which I believe is by Adam Leroy with a paper in preparation. I couldn't find the exact citation, but this is of the galaxy NGC 6300 in CO. So these are observing the giant molecular clouds that are the largest gravitationally bound structures in galaxies, and then go on to form stars and clusters of stars, and are really kind of the fundamental unit of star formation in some ways. But I'll argue in this talk that there's kind of the missing piece of the donut hole in this to connect the smallest scales and the largest scales in external galaxies are observations of the entire Milky Way, that our own galaxy connected to the external galaxies, where because everything is so close to us in our own galaxy, we get a much more sensitive and higher resolution view. This is, of course, as a star formation person, I'm financially obligated to put the Hurt diagram into my talk. This is the Milky Way here with our sun as this little yellow dot. So in terms of the open problems in star formation, I've helpfully taken these from 2 white papers for the equivalent of the decadal survey in Canada, written by James D. Francesco and Eric Rosolowski, that on terms of the 2 scales of both the local Milky Way and extragalactic scales, we have questions of how does dense gas flow to form the sort of embedded clumps that form clusters, the embedded cores that form individual protostars, and the individual protostars themselves? And what physical processes set apart clustered star formation, things like form groups, associations, and clusters, apart from the physics in isolated clouds, which is mainly what we've studied extensively over the last several decades. And we have just incredible amounts of knowledge towards that could be very useful. But on the other side of extragalactic, how are individual sites of star formation like GMCs influenced by their galactic environment? And how does local star formation relate to the extreme mode? So, the run-of-the-mill quiescent type Milky Way compared to the extreme star formation at cosmic noon, where, basically the majority of star formation was taking place at a redshift of 2. How do we reconcile and understand those 2 modes and the effect of the environment on it? And how does the environmental conditions affect the stellar initial mass function and other results of the star formation process? So this is to say, what can we learn and how can we predict things about star formation process beyond, say, just the star formation rate? There's also important things like the initial mass function of stars and things that are important too, that are fundamental to astronomy. So progress in these subjects requires wide field, or at least I'll argue, wide field and high resolution mapping of the Milky Way to connect these 2 scales together, just like the donut hole going in to the donut. It's just right in the middle of these 2 things. So in terms of the Milky Way in dense gas, I'll refer to dense gas because that's the gas that's really important in the prior step to forming stars. Everything is connected to everything else. So things like the diffuse gas, galactic halos, and other things are also important for galaxy evolution and star formation. But dense gas is really the direct previous step to forming stars. And I'll highlight that fast mapping of the 3 millimeter traditional dense gas tracers with the GBT will enable wide field surveys of these molecules in particular that are crucial to tracing the cold, dense gas that will go on to form stars. And the GBT has done a really remarkable job at this, enabled by pathfinding instruments like the K-band focal plane array, which has been a workhorse of surveying, in this case, ammonia, because the KFPA is a 7 feed receiver. It's excellent for mapping large areas. And ammonia is a centimeter wave molecule that is excellent at tracing moderately dense to dense gas. This beautiful map here was taken of the torus L1495 to B218, naming the features going across filament and torus. It's really kind of, the archetypal filament in some ways. And perhaps the largest map with the ammonia ever made. This is 3 degrees on a side, the size of a full moon by this circle, giving us an excellent view of the dense cores that you can see in each of these regions in the boxes. And also of the Green Bank Ammonia Survey that surveyed most of the nearby, the nearest molecular clouds to the sun, like Perseus and others, which I'm showing here with the GBT ammonia on the left and dust emission, or far infrared emission, I should say, from the Herschel space satellite here. And, these are these are enormous maps, degrees on a side. It's remarkable that we can survey whole clouds with the GBT. Here I'll switch gears a little bit to, instead of just individual clouds, what can we learn about surveying the Milky Way in terms of the galactic plane? So this is a map of the Bolocam Galactic Plane Survey that was completed a few years ago, Gary 2011 here, taken on the CSO using the Bolocam instrument. This is 1 millimeter continuum emission, so it's probing cool to warm dust. Resolution is about 30 arc seconds, and it surveyed the galactic plane from minus 10 degrees galactic longitude to 90 degrees galactic longitude, and a whole bunch of outer galaxy fields. And a recently completed large program, or a pilot large program, it could be a whole galactic plane survey, with the IROM 30 meter using their new NICA 2 kids array. It's just somewhat similar in concept to a bolometer, but it's a continuum millimeter receiver at 1 millimeter. But now using a factor of 3 times higher resolution, because IROM 30 meter is a 30 meter telescope, we get the Gaston field with just absolutely exquisite data. Let's see, how can I go back and forward? There, oop. Wow, I mean, for someone who looks at these kinds of data a lot, it's just remarkable the kind of fidelity and improvement that we get this. But the interesting factor, though, is that in this half square degree field that I've shown, half degree on the size of the magenta box, that in this Gaston Continuum survey, they've identified a new population of cold, massive clumps being the kind of 1,000 solar mass clump of gas that goes on to form, say, a cluster of stars. A new population of cold, massive clumps that may be precursors to more evolved protoclusters. And these clumps were not identified in previous Herschel and millimeter observations. They're shown in the white circles on the right. And something that's enabled by the Argus instrument on the GBT, which is a 16 feed 3 millimeter band receiver. Absolutely amazing for the exquisite resolution, like 8 arc seconds that you can get without any spatial filtering, just really a game changer for wide field observing. We proposed for an N2H plus 1 to 0 blind map over a half degree sized field, which is enormous in terms of the kind of dense gas existing data that we have, where N2H plus is really sort of, one of the best for chemical reasons in particular, for the chemistry, is really good at tracing cold, dense gas. And this will help us know how clumps in different evolutionary stages, these early ones, but also the evolved ones too, because we're getting everything, how are they connected to the filaments that feed them on larger scales, and how are they connected to their environments? So this is these tiny little beams are the resolution that we'll have over this full map. And it's something really cool that will be enabled by Argus 144, which is 144 feeds instead of 16 feeds. Proposed instrument for the GBT, very similar to Argus, but much, much faster mapping rate, is that to get to a roughly comparable depth to our field in the cyan, to cover the Galactic Ring Survey, which is a 13 CO observation of the galactic plane using the 5 College Observatory, previously in Massachusetts. This is a map by Reiner et al. 2019b of a reanalysis of it. Really great figure. We could map in about 220 hours the half of the footprint shown in this blue field here, which is kind of more appropriate because the dense gas we wouldn't expect to be as extended as the CO. We have to choose our fields carefully, which would be a total game changer. It's what I meant in the initial part of the talk of connecting the extragalactic scales to the smallest scales would be a dense gas survey of our Milky Way fitting into the center. So in terms of the next generation facilities, besides Argus 144, is that these will open, I think, hopefully I'm not being too bombastic here, but I think they'll open the floodgates to wide field spectral line data of our galaxy more so. And I'll highlight the synergy between the next generation VLA and the GBT in this slide that, I sort of cheekily put here the seventh key science goal for the NGVLA in terms of, our galactic ecosystem of the Milky Way, that, understanding the earliest phases of star formation in its phase progress also needs to understand that star formation in context of its environment, which is sort of a theme that I've been mentioning on all these slides. And just as a overview of what the NGVLA Core, which is a piece of the NGVLA, it's a core collection of closely spaced antennas in the center, which will be exciting for galactic star formations. 94 of these 18-meter antennas, or at least it will be, perhaps, with a maximum baseline of 1 kilometer, which would give 0.7 arc second, sub-arc second resolution at 90 gigahertz, where a lot of these dense gas tracers are around, is about 90 gigahertz. With a primary beam or field of view about 44 arc seconds, about 5 times the collecting area of ALMA in standard subarray mode, meaning that even if you just had the core, it would be 5 times the collecting area of ALMA at 3 millimeters. So the core alone, with fast mapping of sub-arc second imaging of dense gas tracers like N2H+, will transform the study of the cold dense gas in the Milky Way. And that, coupled with Argus 144 for wide field, high fidelity mapping, we'll have, sort of a Gould's belt, which are the nearest clouds to the sun, view for thousands of embedded star forming regions. Here I've shown the GBT 100 meters compared to the 1 kilometer distribution of these 18-meter antennas. Really, it'll be exquisite to combine both the NGVLA data and the GBT, because the UV coverage is so excellent. It will really make high fidelity wide field views possible. And along with next generation facilities too, like GBT Argus 144, NGCLA Core, ALMA 2030, which give wide band 3 millimeter as well. There's a host of other things on the plate, like the Gusto satellite for mapping the galactic plane in C+, very, perhaps the most important cooling line of the ISM. CCAT for the terahertz windows. At last, I'm not very familiar with it, unfortunately. And also space telescopes like Origins and Spica, which would be far infrared and terahertz satellites. So briefly now at the end, as I've kind of talked about sort of the floodgates that would be possible for studying the Milky Way from next generation facilities, I'll review that actually we have a lot of data coming from like the GBT and ALMA and other facilities right now that are really at the limits of what we can do with our conventional analysis techniques. So I'd like to describe what I've been working on with a way to analyze the spectra from molecular clouds in an automated and statistically rigorous way using Bayesian statistics. So you can actually analyze, these surveys that are over square degrees in terms of area. And I primarily made this for an ammonia survey of 70 micron dark, so they're dark at 70 microns, dark clouds for these clumps in the Milky Way. I'm showing here what is essentially a maximum map of the ammonia towards these sort of 1,000 solar mass, 1 parsec size clumps, where actually these are a combination of VLA and GBT data together. UV overlap is also excellent for the VLA and the GBT. And just, wow, yeah, it's amazing the kind of individual filamentary structures that you can pick out with that. Here, I'll just advance though. But the fundamental problem that we're sort of facing, what I meant by conventional versus more advanced techniques is that these clouds are characterized by turbulence, which means that often we have multiple gas components along our line of sight, which translate to multiple velocity components in the spectra. So I've shown here the characteristic ammonia hyperfine structure for what is in fact 2 velocity components. You know, the 5-finger pattern is mirrored for 2 components. And that for conventional analysis, you need to actually fit these with multiple components, not just one component, as is currently done. So if you fit it with one component, it's underfit with a bad fit in red. Here, it's well fit by 2, but you would overfit if you put 3 components into this. It's this little pink fella down here is the overfit one. We need an automated way to do this towards large fields. So I've developed this software and statistical methodology called NestFit to estimate your model parameters, like your column density, your line width, and such, to identify the best fit number of components in a statistically rigorous and automated way. And this is done using Bayes factors, which are the thing in Bayesian statistics that tells you whether one model is more likely than another model. In this case, one model is 1 component, another model is 2 components. It's fully automated without initial guesses or burn-in or other arbitrary convergence criteria. It's a Bayesian approach. So it conditions the data on prior information and also produces full posterior distributions of your parameters for each position in the map. So you have a really good understanding of your uncertainties. And this numerical technique of nested sampling, hence the name NestFit, schemes are robust and can sample very complex distributions, which are often the case. You know, this is available open source now, and the docs are partly in progress at the moment, but they're also available. And this is what I meant by posteriors. You get the parameter distributions for each position of each of the model parameters, like excitation and column density for 2 components that are shown here for the corresponding labels of red and blue, for all of your parameters. And it can, in an automated way, decompose the spectra of entire fields. So here's the multi-components shown in red and blue for the data that's shown in black at each position towards M17 Southwest, taken from the GBT large program Keystone, which was presented in a work by Jared Cohn et al. 2019A. And it, just hit the button and run. It's great. Or at least, sorry, I shouldn't say it's great. I think it's great. And these are some maps of sort of the peak intensity as well as the integrated intensity that you can get at really high fidelity because they're coming from the model and not just the data. You have a lot stronger amount of information. And I'll highlight that here is that, this is something where you have the combination of the robust statistical techniques, of the Monte Carlo is allowing you to be pretty robust to wandering off into bad parts of parameter space, but also the power of conditioning the data on prior information allows you to go to much lower signal to noise than you would be otherwise. So here is a map of the integrated intensity of ammonia of monoceros R2, also from the Keystone GBT survey. This is just taken straight from the data, more or less. But you can see how it's kind of a little patchy and pixelated. Still very much more sensitive than what came before it. But if we analyze the data using the information we know about the ammonia hyperfine structure and all the channels in the spectra, as well as what we know about the line, we can go to, shoot, push the wrong button. Start from current slide. Okay, we can go to much lower and get higher fidelity here. Pretty cool. So here I'll present my summary of the talk that in terms of the open problems we have in star formation, these tend to center around the environments of both protostars in terms of the flows that feed individual cores, clumps and protostars, but also the large scales in terms of like the environments of GMCs in external galaxies. And the GBT and other next generation facilities like ALMA 2030 and the NGCLA are crucial for connecting these galactic scales through wide field and high resolution mapping of dense gas in the Milky Way. And to address some of the large amounts of survey data we're getting with current instruments and will have in future instrumentation, I've developed this methodology, NestFit, to analyze these survey products in an automated and statistically rigorous way using the power of Bayesian inference. It's flexible and can be applied to new models and observations without being restricted by the training data sets. You just need to make new priors. And the Bayesian analysis of spectra that's enabled by NestFit represents a powerful new approach to the study of large surveys. It's automated, but also the study of the ISM at low signal to noise, which will address many problems of star formation at low densities, like how important are magnetic fields and when the gas is magnetically subcritical, and larger scale flows in terms of that. So with that, I will end my talk, and thank you for your attention and joining us for this webinar.
Thanks, Brian. Let's take time for just a couple of questions. Marty, can you see those?
Currently, I don't have a question yet. Oh, yeah, here's one from Samantha. Says, great talk, Brian. NestFit is great. Keep saying it. And awesome NICA 2 data. Are you using Astrodendro or something else to pick out those continuum sources?
For the Gaston survey, I believe they use Astrodendro. I think they also might use something different. I should check that. That would be clarified in Nicholas Paretto's 2019 conference proceeding describing Gaston.
And let me say there was a question from Herschel Gupta about the joint proposals that I should have answered. He says, how are potential overlaps, conflicts handled in the joint proposal calls? Well, once the primary instruments TAC approves a project, that is sent to the secondary instruments for technical review and also to make sure that these conflicts do not occur. That will be resolved at that point. Well, listen, we're a little bit over time. I want to thank everybody for attending and look forward to the next one 2 weeks from now. And you can always get in touch with us through email and look for an announcement of the next one a few days before 2 weeks from now. Thanks very much.
Yeah.